Lecture 2 or Chapter 5, Inventory Control with Uncertain Demand, and this is the second part of Section 3. So now let's have the optimal QR policies subject to Type 2 constraint. Service Type 2 service level constraint. So as you remember in the previous part, I said that the EOQ for Type 2 service level is not optimal, but it's a good approximation, right? But here we want to obtain the optimal order quantity, not the EOQ. So yeah, here we are going to consider the QR inventory model, and we don't have the penalty cost here, the P, but instead of that, we are considering a type 2 service level, the beta. Okay, so if you remember from the previous section, we had these two equations. Equations number 1 and number 2 was where this Q was equal to 2 lambda times K plus P times NR over H, right? So this was equation number 1, and equation number 2 was this 1 minus FR equals Q times H over P times lambda, right? And this was equation number 2. So here, if we obtained P by the second equation, by this, P becomes this. P becomes Q times H over 1 minus FR times lambda, right? And now if we replace this P in the first equation, so as you see here, let me show here, as you see here, we have a P in the first equation, right? And if we replace this P by this equation, so by doing that we are somehow eliminating P, right? And then by doing that, we will have a quadratic equation, and then by solving that quadratic equation for a positive root, then we can obtain this equation here. Okay, so which we call here as equation number 3, and so that will obtain our optimal order quantity. And since we are considering type 2 service level, we have beta, then by having that, we can have this equation as our equation number 4, or the second equation here. So NR should be equal to 1 minus beta times Q. Okay, so by having these two equations now, we can actually do the same procedure like the QR in the previous section. So we'll have an iterative process here, and by doing that, we can obtain the optimal value for Q and R. Okay, and this approach is also called SOQ, or service level order quantity. Okay, we can also rewrite equation number 4. We had this equation before, NR equals sigma times LZ. And now we see that NR equals 1 minus beta times Q, right? So by having that, we can rewrite this equation to be LZ equal to 1 minus beta times Q over sigma. Okay, so now this is our procedure here. At first, same as before, we start from EOQ, so we call this as Q0 here, and then by having this initial value for Q as EOQ, we can obtain R0, the initial reorder point. And so how we can do this? So by having Q0 and using this equation for LZ, we can obtain the value for LZ, and then we go to table A4, and by having the LZ value, we obtain the Z value from that table, and then by having the Z, we can obtain R by this equation. It's mu times sigma times Z, right? Mu plus sigma times Z. So, and then by having Q0, R0, we obtain Q1 and R1, and then Q2, R2. So we follow this process until the value of Q and R converge to a certain value. Okay, so by this iterative procedure, we can obtain the optimal value for Q and R under the type 2 service level condition, okay, and without having a penalty cost, okay. So here we have an example. I think this example is the same example as the one that we had in previous section 2. So yeah, the numbers are the same, and the only difference that we have here is having type 2 service level, which is here we're assuming that it should be 0.98. And so by having that, you want to obtain the optimal value for Q and R. Okay, so you may try the iterative process here, but I will solve this example in our live session on Tuesday. Okay, and also I'll answer this question again in our live session, but you may try by your own to see if you can follow that process and solve this example, but I'll have it in our live session on Tuesday. Okay. So the imputed shortage cost, as you saw here, in the model that we have in this section, we don't have penalty cost, right? I mean, we are unable to estimate penalty cost. So because of that, we consider type 2 service level. And then by having that, we can obtain the optimal value for Q and R by iteratively solving the equations number 3 and 4. Okay, so for example, in our example, by having a 98% for type 2 service level, let's say we obtain these numbers, 114 for Q and 124 for R. So these are this is our optimal solution, right? But if we are curious that what's approximately the imputed shortage cost here. So if you remember, we had this equation for P, and now by having this, we can actually calculate the P as the imputed shortage cost here. So it could be useful somehow if we can see that whether the type 2 service level is appropriate or not based on the value for imputed shortage cost. Okay. For example, in our example for beta as 0.98, we obtained a Q as 114 and R as 124. Okay. So now we are going to obtain that what's the imputed shortage cost here, and we know that H equals 2. 1 minus FR in this example is 0.171. Yeah, from the first example, and the lambda here is 200. Okay, so by having these numbers, we can easily write the equation for imputed shortage cost, which is this: Q times H over 1 minus FR times lambda. Okay, so it will be 114 times 2 over 0.171 times 200, and it becomes this 6.67. So here the imputed shortage cost is $6.67 per unit short. So if we have a sense on this number in our industry and our company, then we'll see whether the beta is appropriate or not. Okay. A scaling of lead time demand. In all previous examples so far, the demands distribution was given during the lead time. Okay, but usually in the real world problems, we usually estimate the demands distribution on a periodic basis. For example, for monthly basis or annual basis or weekly basis. And then by having that, we need to scale the demand for the lead time period. Okay, so here we assume that the demand on periodic basis is estimated as a normal distribution, and then by having that we can scale that demand distribution for the lead time period. So here let's assume that the demand is normal for that period, let's say a year or a month, and the mean is seen to be lambda and the standard deviation as nu. Okay, and we know that the lead time duration here is tau. Okay, so by having that, if we want to obtain the normal distribution of demand during the lead time, so mu as its mean and sigma square as its variance, so mu will be lambda times tau. Okay, and sigma square, this, the variance of demand during the lead time will be the variance of demand during that time period times tau. But here should be careful that the time unit of tau should be consistent with the time unit of our base period. Okay, and so by having that, mu is lambda times tau, and sigma equals nu times square root of tau. Okay, so let's have an example here. Here we have estimated the weekly demand for a certain type of automotive spark plug in a local repair shop as normal distribution with a mean of 34 and a standard deviation of 12. Okay, so here actually the lambda is 34 and the nu is 12, and it's for I mean our period, base period is based on weekly periods. Okay, weekly. Okay, so here the procurement lead time is 6 weeks. So the lead time period is 6 weeks. So the tau here is 6 based on the weeks. Okay, so in order to obtain the mu and sigma of demand during the lead time, we can do this. So mu will be lambda times tau. So lambda is 34, tau is 6, so it becomes 204. Okay, so the mean demand during the lead time will be 204, and the standard deviation of demand during the lead time will be nu times square root of tau. Okay, so this means we need to multiply 12 by the square root of 6, and it becomes 29.39. Okay, so yeah, it's so easy. By this procedure we can scale demand for any period for estimating demand during the lead time. Okay, for the scaling demand for the lead time period, we assume that the lead time period is constant, and the only random variable here is the demand, right? But what if the demand, what if the lead time period is a random variable as well? I mean, here we do have two random variables. Demand is a random variable based on the base period, and the lead time period, the lead time length, is also a random variable here. So here, this is what I mean. We mean that demand during the unit time is assumed to be a normal distribution with mean of lambda and variance of nu square, and the length of the lead time is the tau is also a random variable with normal distribution, and the mu tau and sigma square tau is the mean and the variance of the length of the lead time period. Okay, so in that case, the demand during the lead time will be a normal distribution as well, but this will be the mean of demand during the lead time. Same as before, we just need to multiply the means. I mean, lambda times mu t, that's it. But that's totally different for the variance. The variance will be this, mu t times, I mean, yeah, mu t times nu square. So this means mu t is the mean of lead time length times the variance of demand during the time, the unit time, and then plus lambda square, the mean of the square of the mean of demand during the unit time times the variance of the lead time's length. Okay, so that's how we obtain the mean and the variance of demand for normal distribution of demand during the lead time if the lead time length is a random variable with normal distribution.